All right, in this video, we're going to talk about Hyperblock scheduling, and this is the last video on global acyclic scheduling. Let's say, so the idea of Hyperblock scheduling is that it's going to merge together all of the other techniques we've learned so far into kind of a single, approach. So it's going to integrate trace-based scheduling, sentinel scheduling for loads, superblock formation with tail replication, and predication all together into one big technique. And really, the key concept behind Hyperblock scheduling is that we need heuristics that guide when we apply these things and how we do it. Okay, so here's an example of a Hyperblock. Let's say we start out with some code like this. It has several conditionals. And when we made superblocks, we could only follow one path through the code. And that's a problem because that means if we exclude the path from C to D, and if that's a very heavily weighted path, then our superblock is only effective, a fraction of the time. But what we do with a hyperblock now is to include both of these paths, and we can do that using predication. So now we would have one big block that has A, B, C, D, E, and F, and B and C would be predicated on the condition in A, and E would be predicated on the condition in D. Okay, but since D is control independent of A, and since F is control independent of A, then D and F don't need predicates. Right, so these stars I've put here on each block indicates which blocks have to be predicated and which blocks don't have to be predicated. Right? And the key idea behind predication is we're converting control dependencies into data dependencies. Okay, so this is what our overall hyperblock would look like. We would have all the instructions here in one big block, and then we would perform cycle scheduling on all of these instructions at once. And this might allow instructions in F to get moved all the way up and execute at the same time as instructions in A. And so hopefully if we do something like this, we can get a much tighter, a much higher performing instruction schedule than we would be able to otherwise. One thing to note is that we're not allowed to have any branches that go out of this trace and come back into it, right? We're not allowed to have branches that come back into a hyperblock, right? Part of the superblock requirement is that there are no side entrances, and hyperblocks have the same requirement. Okay, so if there is a cycle, it has to go back around and start at the entry to A. Okay, so that brings us to the first step of hyperblock formation, which is region identification. So a region for a hyperblock will be a set of blocks dominated by a single header that have no control flow cycles except possibly for back edges to the header. Okay, back edges are allowed because they're not side entrances, they're just side exits. And side exits are perfectly fine. Okay, so for example, this could be a region A, B, C, D, E, and F. There are two back edges, but they go back to the header, so we can just treat them as side exits, not side entrances. Okay, then we do something called back edge coalescing, and that is we try to make all these back edges in the graph point to the same block. And that just is going to make it easier for us because when we do have to branch out of the hyperblock, we can just have them all, at least for this particular region, we can have them all branch to the same block G. Okay, now the next thing we have to do is block selection. And this is actually the tricky part because we have to trade off several competing concerns, right? And one of the previous videos we talked about predication and the fact that predication may not always be beneficial, that it comes at some added costs. And so the idea of block selection is that we want to figure out what blocks we should include in a hyperblock and which ones we shouldn't, taking into account the cost that may come along with that block. So in general, we want to favor adding blocks to the hyperblock because that should mean we get more instruction level parallelism, right? We get more instructions to select among. And so hopefully we can come up with a better schedule. So this tells us we should prefer to add blocks in general. However, adding mutually exclusive blocks means more resource contention on registers and issue slots. So we only want to add mutually exclusive blocks to the extent that it doesn't drastically increase resource contention. Okay. Also, adding infrequently executed blocks, and if we're predicating infrequently executed blocks, then that means we're just fetching a lot of instructions all the time that never really get used. And so adding infrequently executed blocks just means more overhead, and we want to limit the degree to which we just add more overhead. Okay, and then there's another idea that comes into play here, and that is we want to avoid hazards. So a hazard is anything that limits optimization. So for example, a function call, a subroutine call, is a hazard because you'll actually leave the trace and go to that subroutine. and that could be bad. So we don't want to build a hyperblock that includes a subroutine call in general. It's bad. It's bad only in the sense that it limits optimization, right? It's not bad for any other reason. Okay, also, there are cases where you can't analyze relationships between loads and stores, and when you don't know the relationship between a load and a store, as we've seen in previous projects, you can't reorder them as aggressively or optimize as aggressively. And so if you don't know what's happening between loads and stores, you might also have to limit the amount of optimization you do. So if we have these harmful kinds of memory references, we may also want to avoid placing them into a hyperblock. Okay, so these are concerns we have. And based on these concerns, what we do is we come up with what's called a block selection value. And this block selection value tells us, is meant to kind of capture these various competing elements to tell us, should we put a basic block in the hyperblock or not? Okay, so this equation has several components. And this I here is referring to a specific basic block. Right, so we're going to calculate this based on the characteristics of some particular basic block in the program. Frequency of I and size of I are the execution frequency of the basic block and the cost and instructions of the basic block, respectively. Right, so here we're talking about how often does the block execute, and here we're talking about we're asking how big it is in terms of the number of instructions. And then size of main and frequency of main are the cost and frequency of the path that we've already turned into a hyperblock. Right, so size of main would be the number of instructions total in the hyperblock, and the frequency of main would be the frequency with which that hyperblock executes. And then BB characteristic, BB car, this estimates the number of hazards. So for example, 1 might mean no hazard, and 0.25 would mean a serious hazard. Right, that this instruction is really going to cause problems for us. Okay, now when we evaluate this equation, and I'll talk about that just a little bit more next, when we evaluate this equation, what we want is a bigger value. So bigger is better in the final result. And let me explain why. So what we want is to add blocks to our hyperblock that execute about as frequently as the rest of the hyperblock, because that means you're getting work that's going to be useful most of the time. So if the frequency of the block divided by the frequency of the hyperblock is really close to 1, if their frequencies are the same, then this number will be bigger, right? It'll be close to 1. But if the frequency of the block is really small compared to the frequency of the hyperblock, then that means it's not executed often and it's just overhead. So this will be a low value. So a low value we can interpret as creating overhead and not being good, whereas a high value we can interpret as executing a lot and being very good. Right? So in general, we want this number to be bigger. Okay, and then here, size of main divided by size. What this is saying is that when I add a block to the hyperblock, I don't want it to dominate the size of the whole hyperblock. Right? So I want to tend to add modest sized blocks into the hyperblock. In other words, I want the size of the block I'm adding to be less than the size the hyperblock is already. So if my hyperblock's already 20 instructions and the size of the block is 5, then 20 divided by 5 would be 4, and that would be a big number. And so that's kind of what I want. Whereas if the size of my hyperblock is 10 instructions and I'm considering adding to it a block that's 20 instructions, then this is generally seen as not good because this single basic block would be dominating most of the execution cost of the hyperblock, in which case it probably doesn't need to be added to the hyperblock. It's a big enough block on its own that you don't need to do anything else for it. Okay, so you tend to want this number to be big as well. You want the size of the existing block to be able to absorb the block you're adding. The idea being now if it's relatively small, you'll be able to find slots in the schedule for it. Okay, and then BB characteristic, this is just a number we make up to represent other hazards. It's just designed based on intuition. So for example, if a basic block has a function call in it, we'll give it a value of 0.25, but if it doesn't have a function call, we'll give it a value of 1. And that's what I'm going to do in my examples. But you could make this last number be arbitrarily complex to try to reflect the degree to which things in that block are going to limit optimization. Okay, so to recap, we want this number to be big because we want a frequently executed block. We want this number to be big because we want relatively small blocks. And then we'll set BB characteristic high when it's a good choice and low when it's a bad choice. And so when we multiply these three terms, the bigger the better. And then our rule is that if the block selection value is greater than 1, then we're going to keep the block. If it's less than 1, we're not going to keep the block as part of the hyperblock. So here's how it works. Let's say we have this control flow graph. And now what I've done is I've annotated each edge with the profiling weight, the frequency of that edge. And in each basic block, I've put the size or cost and instructions, and then the K, which is the BB characteristic that I showed you on the previous slide. So we have all the data we need for all the blocks and all the edges in the program. And then what we do is we start by making a hyperblock. I'm sorry, a superblock. And a superblock is typically made out of the most frequently executing edges. So maybe we'll start with A, B, and D. And so this is our seed superblock. And it's just given that we're going to have A, B, and D. And then what we do is we look at the edges that leave the superblock, A, B, and D, to see if we should include the block that's along those edges or not. Okay, so let's take C. Well, when we evaluate this equation, then we see that C has an execution frequency of 40. The superblock we start with has an execution frequency of 55 because that's the least weighted edge in the superblock. So the first term of the block selection calculation is 40 divided by 55. The frequency of C divided by the frequency of the block, of the hyperblock. Okay, then the next term is the size of main divided by the size of the block. Okay, to get the size of main, we add up the size of A, B, and C. And so that's 8 plus 12 plus 3, and so that's a total of 23. And then we divide it by the weight of block C, which is 15. So that's 23 divided by 15. And then C has a block selection value of 0.25, and that's because C has a subroutine call in it. And if you go back, well, let's just assume it's because it has a subroutine call. And so when we calculate this all out, then we get something like 0.278, and so we're not going to keep block C. We'll decide to exclude that from the hyperblock. Okay, block E, on the other hand, it has an execution frequency of only 5, and so the first term will be 5 divided by 55. It has a size of only 2, so we multiply this times 23 divided by 2, and then it has no concerning features because it has a K of 1, and so that produces a value of 1.04, and this is above 1, so we'll keep it. So what this analysis does for it in this case is it says, well, we're saying it doesn't execute often, but it's very small. And the fact that it's very small means we can absorb it into the hyperblock without it costing much. And so we keep it. Okay, and then we have F. Now, when we add E into the superblock, then the superblock's frequency of execution now actually involves two paths. And both of those paths flow into F. So that means we should consider the combined probability of all the edges flowing into F. And so that would be 60. So the probability of F executing is 60, and now the weight of the superblock would also be 60 because it includes both of these paths. And so it's 60 divided by 60. And the weight of F is 7, and the new weight of the hyperblock is 25, so 25 divided by 7. But then F has some bad characteristic. So that forces us to multiply by 0.25. And it's all, this big factor here, 25 divided by 7, is almost enough to get this block chosen, but it's not quite there, so we discard it. Now, admittedly, the threshold against 1 is arbitrary. It would actually have to be tuned over a large number of workloads. So actually, if you tuned it enough, you might decide that really the threshold should be at 0.8 and that this block should be selected. But just for the sake of the example, we're saying we're going to discard this. So the only block we're going to keep now is block E. Okay, so that leads to the hyperblock made up of A, B, E, and D. F is excluded. And we have a side exit to C, And that means we have to do tail replication on all the blocks that C can reach, which includes B, E, and D. And so now we have duplicate copies of B, E, and D in the event that we take the side exit to C. Okay, this is just like superblock formation in that whenever you put something into a superblock, then you once you leave the superblock, you have to perform tail replication to have access to the remaining blocks needed to execute. This does result in code expansion and code cost. Okay, now what we do is we look at the blocks within our hyperblock and we add an appropriate predication support. So every block that needs predication will get its own predicate register. So E will get a predicate register and D will get a predicate register. In this case, let's say P1 and P2. So every instruction in E will be predicated on P1 and every instruction in D will be predicated on P2. The exit branch to C has to be left on the code, but the branch to E and D is not left in the code. It is eliminated because now we have this predicate calculation instead. Okay, and when we do final scheduling, the predicates are going to be handled as data dependencies like all of the registers. Okay, and then what we do is we perform cycle scheduling on the hyperblock using our favorite heuristic, like possibly depth-based scheduling, and according to some constraints. Right, we have to treat the predicate register as an additional data dependence. We can use sentinel scheduling to hoist loads above branches, right, above side exits. This requires, when we move a load up, we need to mark it as speculative, and then we need to leave a check instruction after the side exit. Okay, branches must execute. Any branches must execute after all the instructions in their own block, or you'll have to do some compensation code. And there are some other optimizations we could do. For example, one thing you could find out by going and reading the literature on VLIW is it is possible to do speculative load hoisting above stores, but I'm not gonna talk about that optimization. Okay, so let's say that we have this code. This is a very similar graph to the graph we've been looking at, but now I've actually specified what the code is that's inside of here. And I've labeled edges with probabilities, and you'll see here that block C has a jump to subroutine, and so we'll consider C as a not very good block for that reason. Okay, so the first thing we do is region identification, and we can form a region out of A, B, C, D, E, and F. And then what we do after we do that is we redirect back edges so that we have this extra block here in case we need to form some sort of tail replication. We'll have this block that the tail can branch to then go back to A. Okay, we do block selection. We form a superblock, then add additional blocks. So the initial superblock here would be A, B, E, and F possibly, because that would be the high probability path, right? We have a 90% edge here and a 55% edge here. And you may or may not want to just automatically assume F is involved, but A, B, E, and F is a reasonable place to start. Okay, and then the question is, what do we do with C and D? So we can calculate the block selection value for C, and when we do that, we're going to get something like 0.13, and so we'll exclude it. And when we calculate it for D, we get something like 3.6, so we'll keep D. And that leads to this overall code structure. We have A, B, D, E, and F as our hyperblock, and then we have to tail replicate the code from C on. Okay, now we merge all the blocks that execute conditionally and provide them with a predicate. So D and E will have predicate registers. A, B, and F do not need them, right? Because A and B are, if there's actually a branch that takes you out of the hyperblock if you're not supposed to execute B, so we don't need to predicate B. If we're not supposed to execute B, we'll just exit the block. On the other hand, D and E have to be predicated because they're dependent on this branch. So they'll get, this branch will be removed, we'll calculate predicate registers, and D and E will be predicated. And F is control independent of B, right? F post dominates B, so we don't need to predicate F. They can just execute normally. Okay, so that leads to this big hyperblock. So that would result in code that looks something like this, right? So we get rid of the branch and we insert this comparison instruction that's going to produce two predicates. And then these predicates are placed on the instructions from the two basic blocks that needed them respectively. So we either have P1 on this block, on these instructions, or P2 on this one. We still have the side exit branch to block C, and then we have the exit to block F. And of course, anywhere I'm using P0, P0 is always true. So it's basically like not having a predicate at all. And then what we do is we take these instructions with these predicate values and we cycle schedule it as aggressively as we can while being sure to perform any code compensation that has to be done. Okay, so I think I cycle scheduled this correctly. If you spot some error, please let me know. But I just took this code and I cycle scheduled it on a 2-wide VLIW. Now, one thing you'll notice is that these instructions from way down here at the end got moved very early in the schedule. And because of that, I update R0 before evaluating the branch to go to C. And as a result, I need some compensation code. I needed to place my value of R0 temporarily into another register. And I'm noticing I made a little mistake when I did that. Let's just fix it. So this should be R2. Okay, and then so R2 is used to compute R1, and then R1 is used to evaluate the branch. Now if we take the side exit is going to do the exact same calculation all over again, but it doesn't know it's already happened once, and so it's just going to repeat it, this time using the correct original code from block F. The other thing you'll notice in here is that I used speculative scheduling of loads several times, sentinel scheduling, so that I could move these loads up to execute earlier. And since I moved them up above the side exit for C, then I need to place S. I need to place this S on them, and then we can check them to make sure they didn't trigger any exceptions here after the side exit. Because once we pass the side exit to block C, we know those loads should have executed, and we know that we should check them. Okay, but why did these loads get moved up before the side exit? Why not evaluate the side exit first? Well, if the idea is that most of the time we stay in the hyperblock, then we want to prefer to shorten the hyperblock as much as possible, as opposed to shortening the side exits. We're assuming the side exits don't happen, so we actually delay them. You know, it might be reasonable to delay them quite a bit. Now, at the same time, according to my code, I was showing this side exit as only having a 10% probability. So it makes a lot of sense to penalize when the side exit executes in favor of shortening the 90% case, right? The 90% case that you're going to stay in the hyperblock. Now, if you went back and you went to my original control flow graph and you cycle scheduled each block independently, and then figured out how long that schedule would be, it would be several times longer, or it would be at least twice as long as this schedule. So it might be an interesting exercise for you to go and do to see what the benefits of this global scheduling actually were. It'd be very hard to get a schedule this compact without doing a hyperblock schedule and without using predication. Okay, so in summary, hyperblock scheduling identifies common paths through the code and schedules them aggressively. You need several complementary techniques to make this work. You have to avoid side entrances to make scheduling simpler. You need good profiling to influence the goodness of your hyperblock selection, right? We need to know accurate weights of which edges are more likely to execute. That's really important for our block selection value. It's really important for the initial super block, that we start from to do hyperblock scheduling. We need sentinel scheduling that lets us aggressively move loads above side exits. And we need predicated execution so we can follow multiple paths within the same hyperblock. And what all these things together require is you're going to have to have some extra hardware support for sentinel scheduling, for handling loads aggressively, and for predicated execution. Okay, now what about loops with complex control flow? What if what do we do to make them execute more efficiently? Well, what we could do is form a hyperblock and then modulo schedule the entire hyperblock. This is a reasonable thing to do. Or you could form multiple paths to the code and then software pipeline each path independently under the assumption that you'll stay within that path as you go around the loop. Okay, or you could just unroll the loop a lot of times and then use acyclic scheduling within the unrolled loop. Like use a hyperblock within the unrolled loop to get more performance. Okay, the last one is probably the simplest thing to do, but it's also going to lead to it's also going to lead to some code bloat even beyond what a hyperblock normally causes. Okay, so in summary, instruction scheduling's overall goal is to make a program run efficiently within the given hardware resources. I presented a lot of approaches for VLIW in the last several videos, but it can work for other superscalar or in-order processors, right? If you're running on a dynamically scheduled processor, then the amount of role the compiler can play is less because the hardware is going to be doing a lot of work trying to schedule instructions in the right order. And so the extra effort by the compiler may just not help much. It may help a little bit, but it's not going to help a lot. But especially on in-order processors, even if it's not a VLIW, if it's just a regular in-order processor with then the compiler can have a big role in seeing to it that things execute in an efficient order. There are a lot of things that could be studied yet on instruction scheduling. Okay, this is not a solved problem. It's very heuristic driven. There are always refinements and improvements that could be made. For example, how do you do global scheduling for wider scopes, like at an interprocedural level? Instead of just looking at multiple blocks within a function, can you look at multiple blocks across functions? How do you deal with latencies that aren't fixed, like floating point and memory? How do you handle more complex restrictions? How do you merge with other optimizations, especially register allocation? And in the next couple of videos, we'll see why this matters, why this might be a really important one to get right. And then also, and a problem that's very interesting to me, is how do you schedule instructions across multiple cores or across threads? It's another challenging problem. But if you could do this well, if you could divide up a program and schedule it across multiple cores rather than within a single core, you may be able to get a lot more performance. Okay, so that's it on instruction scheduling, and we'll start talking about register allocation next.